on. You live on campus, don't you?
Yeah.
Yeah. Fine, dude. Let's have a look at the simple harmonic motion homework and the pendulum homework and the electricity homework. So we have 3 homeworks we need to do. Huh. We have a double class now, don't we?
Yeah.
Yeah, okay, so we should be fine. Right, so firstly, the simple harmonic motion. Okay. I need my calculator. Where's my calculator? Oh, here we are. So a pendulum is swinging left and right. It swings a distance 5 centimeters. And it takes 2 seconds for each swing. How fast is it traveling after 5 seconds? Okay, so what you have here, you have this going back and forth, so this is like simple harmonic motion. Left, right, left, right. So we know that the time is 5. The amplitude is no, the time is 2 and the amplitude is 5. 2 seconds, amplitude 5 centimeters, 0.05 meters. So we can get the omega. The omega is 2 pi over t, 2 pi over 2, 3.14 radians a second. So the velocity, now let me get this right, we need to use it's starting at its furthest point, so the velocity formula is A omega sine omega t, and here the t is 5 seconds, so 0.05, 3.14 sine 3.14 times 5.
When do we have to use sine and cos?
I said that in
I forgot.
I'll tell you in a second.
The t is 2 seconds.
Yeah, but I said that in the question
Yeah, 5 seconds.
after 5. Radian mode. It's quite small. The speed is 1.25 millimeters per second. It's going quite slow at this time. Just a second. Do you know what? I'm going to change this a little bit. I don't like the 5 seconds here. I'm going to change it to 3 seconds, okay? So here I did 5 seconds, but I'm not liking that, so I should have picked a better number. So I'm going to make it 3 seconds. So if I make it 3, we get a more respectable. Oh, that's even smaller.
Yeah, obviously it will be.
It's going to be small, but I don't want it to be that small. Hang on, let me think. It takes 2 seconds to go.
It has to be shorter.
Yeah, I'll make it half a second. Yeah, that's better. Half a second. You'll get a very speedy 0.157, and that's if you use after half a second. Yeah, I mean, if you did it the other way, that's fine. It's just the answer's so small, it's just pointless. So half a second is what I'm going to do this time.
Is it mm per second?
No, it was previously because it was so small, but now that's actually, yeah, you're right, sorry, it's now proper meters per second. Okay, next question. 50 gram mass at the end of the spring. The guard pulls down on the spring and it bobs up and down. At distance 10, she releases, it starts to bob up and down. 3/4 of a second. Right, so what's happening here? She pulls down on the spring at distance of 10 centimeters and releases, so it's going to go back up and down and up and down. So the amplitude is 10 centimeters. The 0.10 meter. The time is 3/4 of a second, and the mass is 50 grams. And that's all we know. That's all we know. Okay, so the first thing is, what is the omega? So the omega is 2 pi over t, which would be 8.378 radians a second. B, what is the acceleration after 1 second? So here I need to use the formula. Now, if I want to be really careful about my signs, we'll call this direction here plus and this direction here minus. No, we can if we want, because it's easier to say that it starts at plus. But if you want to do it the other way around, that's fine,
Yeah.
if you prefer. So then in this case, the A, instead of being minus A omega, now normally the formula, hang on, let me just think, it starts at the far side, so it's cosine cos, minus A omega squared cos omega t. Now, this isn't quite the formula here, because in this situation, when the particle is down in the negative, which way is the acceleration?
The other way.
Up, positive.
Yes.
So the sign is backwards here because it starts at the negative instead of starting at the positive. But usually for the exam, not always, but usually we don't have to worry too much about the sign in this question.
Can you put plus minus?
Maybe not here. Let's worry about exam questions later. A is 0.10. The omega is 8.378 squared cos omega, and it's after 1 second, so t is 1. Minus 3.5 meters, minus 3.51 meters per second squared. Okay, the C part is, what is the force after 1 second? Is the force up or down? Yeah. So, yeah.
Again minus?
The calculator gave me minus, which tells me that after 1 second the particle is up here and it's accelerating downwards. The C is, what is the force? Well, that's just Newton's law. F equals ma. And I know the m, and I know the a. So, just put the two together. And you get minus 0.175 newtons. D, is this force upwards or downwards? Well, clearly it's downwards.
Because it's minus.
Because it's minus, yes.
It's pulling it downwards.
Yes. What is the force the spring is providing? Now you might think, oh, well it's 0.175 downwards, but no, because there's also gravity pulling it down. So if we look at the picture very carefully, what's happening here, this is the equilibrium position, and the spring is going up and down here. And in our picture, when the spring is here, there's a force downwards in total of 0.175. Hey guys, come in. Are you all together?
Yeah.
What happened to you?
Trouble.
Where?
Just from beginning.
Yeah, from beginning.
Were you on the 122?
No, we take 1 to 0 and then change to 9.
Okay. I'm doing simple harmonic motion homework. Okay, so like we were saying, the total force down is 0.175 newtons. You'll be okay, Grace. Be strong.
I have a headache.
Oh dear. No breakfast?
Big headache.
Big headache? You shouldn't call Amanda a big headache. Yeah. You went to sleep. Me too. Me too. Okay, so downwards is 0.175 newtons. But there's two downward forces. Well, there's the downward gravity force, mg. Yeah.
Yeah.
And what's the other force here? Well, there's the force from the spring, isn't there? In this case, the spring is pushing it down because it's past the equilibrium. If the ball was down here, the spring would be pulling it up, and if the ball is up here, the spring would be pushing it down. Yeah. This is the last part of 2. Last part. So you have F plus mg equals 0.175. F equals 0.175 minus mg. So the answer is minus 0.3155. Now what's strange here is that minus tells me that the spring force is actually acting upwards, that I drew the picture the wrong way.
No, but the force 0.177 is minus.
Yeah, but what's happening here is I'm saying the two downward forces equal this downward force. Do you know what I'm saying? So like it's like me saying if this was minus, it's like me saying this plus this equals this without the minus.
Yeah.
And without the minuses here. So because I got a minus here, it means I drew my F the other way around. In fact, the spring is pulling it up. But it's not important. In fact, it's not important at all because I just asked what is the force, or I mean to say how much of a force. So the answer is 0.316 newtons of force. You'll have to watch the video, you two, okay? Because I'll start number 3 from the beginning. Now there's no point, there's no point in writing this down because it's the last part of the question. So you can just watch the video to get number 1 and 2, okay? Yeah. So we'll start from number 3. So you have a, how big is that? 100-ton train with a soft bumper. When the train is parking, its bumper hits the wall. It takes 250 milliseconds for the bumper to compress 2 centimeters, and a further 250 for it to decompress the same 2 centimeters. When the bumper is fully depressed, it has potential energy stored in it. How much energy is stored in it? Where does this energy come from? Okay, so I'll try my best to explain this one. Have you taken the train before? In Ireland? No. Have you ever seen the front of the train? There's like 2 big circles at the front of the train. And when the train is parking against the wall, they push up against the wall. They're like little bumpers. Do you know what I mean? I'll try and draw it. No, I won't try and draw it. I'll try and get a picture for you in a minute. It's like a car bumper when it stops against the wall. It's like soft, so the train can be pushed against the wall when it parks. I mean, you've probably, I'll try and draw it here. You've probably seen them on the track. So it goes across like this, and then at the end there's a wall, and then on the wall there's two little bumpers sticking out with two circles on them, and then the train has two of them as well, and it pushes against it. Do you know what I'm talking about? Amanda, you have no idea what I'm talking about. Train bumpers stop. I don't know. Buffer stop, maybe. Yeah, that's what I'm talking about. These two things.
To push the train go?
To stop the train.
Stop the train. The train can stop by itself.
Yeah, but to stop the train and make it push, like have the train press against it. You know, like I know the train stops itself, but it's to make the train line up to be right beside the wall, nicely parked. You know. Now look, you see this little part here?
Yeah.
This moves in a little bit. Yeah. Compress. Yeah. So they're like springs. That's my point. Yeah. So what happens here? Where are we going? Back here. So what I'm saying is, when you look at it, the picture, it takes 250 milliseconds to go in, and then 250 milliseconds to come out. So it's like a spring. It goes in and then back out. So the time here is 500 milliseconds, or half a second, for this spring. Now, I think I tell you the amplitude as well. 2 centimeters.
The time has to be the time that
A full
compresses
in out, yeah. Now, what is the amplitude? 2 centimeters? No. How much is the amplitude? 1 centimeter, because that 2 is all the way in and all the way back. So the amplitude is, if this is the center, the amplitude is 1 centimeter. So we have A equals 0.01 meter. So I gave you the formula for the energy. We want the energy when it is here. So, do you have the formula for how much energy it is? I think, do you have the formula? It's like 1 over 2 m omega squared x squared. So here the x is 0.01. Or s, it doesn't matter, x or s, whatever. Now, we don't know the omega, but the omega is 2 pi over t. So that's equal to 2 pi over a half. So that's equal to 4 pi. So this is a half, 100,000, 16 pi squared, 0.01. So the energy that's stored in the spring should be a lot. But this is not surprising, because it's a big train and a big spring.
Why A is 0.01?
Yeah, because that 2 is the distance from the full left to the full right. So it's only 1 from the center. That 2 is all the way in and out, but we should measure from the center.
Just
the center of the motion. Yeah. So you get a 79, basically 79 kilojoules, 79,000.
Just the motion will go back and forth to the front.
Yeah. So the and we get the energy here, and then the spring comes back out.
So we just calculate the energy go in. We don't.
Yeah, we just want the energy when the spring is fully compressed. By the way, where did this energy come from?
Train.
From the train moving. What type of energy is that?
Inertia.
Oh, come on, give me the right word.
Potential energy, electric energy.
So the kinetic energy of the train was converted into potential energy of the spring. So this train had a kinetic energy.
But how the spring has potential energy?
The spring is compressed. There's energy stored in the compression. Yeah. Now, you could actually work out how fast the train was going when it hit the bumper. Because you can say that the potential energy here should equal the kinetic energy of the train. Can I go down? So, I don't ask it in the question, maybe I will next time, but the train is moving and then it hits the spring. So the potential energy here equals the kinetic energy here. Make sense? So you have a half mv squared equals 90,000, and when you solve that you get v is 1.26 meters per second, which is actually pretty fast, maybe too fast. Yeah, I made my numbers too big. It's pretty fast to hit the spring. How fast the train is going before it hits the spring. Okay. So yeah. Okay, next one. A spring is displaced 5 centimeters and it vibrates with 2 hertz. How fast is it going after 2 seconds? It was displaced a distance of 10 centimeters instead. Okay, so in the last one, what you have this spring. It's going up and down, and here the amplitude is 5 centimeters, and the frequency is 2 hertz. Oops. So the frequency is 2 hertz, but the time equals 1 over the frequency, so that would be 0.5 of a second. Yeah? Okay. So next I then say, how fast is the spring travelling after 2 seconds if it was displaced a distance of 10 centimeters instead? Okay, so if I go back to my picture, so if instead I pull it down further, so this time it has an amplitude of 10 centimeters. Ugly. It's 5 centimeters, and here it's going up and down. So now it'll have an amplitude of 10 centimeters. What I I don't remember if I told you this. I think I might have mentioned it before. Do you remember when you have the forced harmonic oscillator? Do you remember it when you shake it? Anyways,
Yes, the resonance.
I'll tell you, I don't remember saying it, but I'll tell it to you now. It's a useful result, and we'll see the proof of this in semester 2. But I won't prove it now, but I'll tell you the result now anyways. If I pull down on this more, okay, or if I shake this more, the times, they don't change. In other words, my point is the time does not care about the amplitude. So in other words, if I pull the spring down more, it will still take the same time to go up and back down. Which seems amazing, because you think that if you pull the spring down more, that should be maybe more time or less time. But in fact it's the same time. The proof of that will be in semester 2.
Just remember.
So for now, you can just remember that the time doesn't change even if you pull it down more. So that was my little trick here to the last one. That the time in the second picture, here, the frequency is still 2. Which means the time is still a half. And what I want is the speed when it's moved after 2 seconds.
It's 0.5.
Oh, sorry, thank you. So the formula is B equals A omega cos omega t. So V equals 0.10. The omega is 2 pi over t, and it's cos, and the omega is 2 pi over t, and the t is 2 seconds. So I'll get my speed now. So I got 1.26 meters per second is the speed. Yes. Okay.
Yeah, but just a question, like,
Yep.
it's not related to, like, it is this ideal situation where, like,
Yeah, realistically it will
it will
slow down and other things
yeah,
too.
okay.
But still, the principle is still true that the time does not depend on the amplitude. I know it seems odd. It really feels like the time should be different if you pull it down more.
But it's like Newton's first law. Everything, like, continuous state of rest or motion, like a ball is rolling, it keeps on rolling forever until it stops.
Pause.
Yeah, like it's ideal.
Pause. Grace, are you okay? Do you need to go to the bathroom? Do you need medicine? Are you sure? Okay. Alright, next homework then. Yes.
Is that in the middle or in the top?
At the bottom. Or at the top, it's the same thing.
But
And it's
maybe we usually use
Sign, yeah.
sign,
Compared
not
to
cosine.
log.
You're right. Thank you. Thank you, Amanda. Okay, so, yeah. Well then I'm going to change the time a little bit. You're right, Amanda, I should have used sine. I'm going to make the time for the last one, oh, 0.7 of a second.
If you change the second one, you change the first one also, right?
No, the question I'm changing. I'm going to say what is the speed after 0.7 of a second. Okay, so that will give me 0.74 meters per second. Okay, next homework.
Where is the t equal 0.7?
I changed this time because if I use this time, I get 0, which is boring. So boring.
What's the zero?
Zero's fine. It just means it's at rest. But that's boring. Okay, can we do the pendulum homework? Yeah? Okay. I'm going to close this.